Oh, hello, my dear students of class 11. Today we will be continuing with valence bond theory. So under valence bond theory, we will be discussing about orbital overlap concept. So here in orbital overlap concept, what you have to remember is I have taught you about the shapes, okay, the shapes of S orbital, P orbital, D orbital, and now whenever they are involved in bond formation, what kind of overlap takes place and under what conditions. So those are the things that we are going to discuss today. So orbital or overlap concept. Now here you have to remember that whenever an atom has unpaired electron, okay, the presence of one or more unpaired electron in an atom, okay, whenever it is present, unpaired electrons are present in the valence shell of that particular atom. So what did I say? I said if an atom has what? Unpaired electron in its valence shell, then they can overlap to form the bond, and this is the cause for the chemical bonding. So the main point here is what? The main point is there has to be presence of unpaired electron. So last time I have taught you. Now suppose this is the p orbital. Now whenever each orbital is occupied singly, now this is unpaired electron. Okay. Now once it has another electron over here, then it becomes paired. So for the formation of chemical bonding, what is necessary? The presence of unpaired electron. That means it has only one-sided. Either it is having only one electron which has spin pointing upward. Okay. Now let's discuss about various postulates of this particular theory. This theory, orbital overlap concept. Now the first thing, as I told you, now whenever an atom has unpaired electron, okay, unpaired electron, then it has its tendency to form covalent bond, okay, to form covalent bond with the electron, and here the electron has to be oppositely spin. One has to be pointing up the other one. The other electron of another atom has to be pointing in the downward direction. So now whenever there is this possibility, then they come together and form chemical bond. Okay, chemical bond. And number 2 point that you have to remember: whenever atomic orbitals of each atom they come together to form this overlapping. One is pointing upward, the other one is pointing downward. Then it results in the formation of molecular orbital. Okay, it results in the formation of molecular orbital or covalent bond. So the first point is the atom with unpaired electron can overlap with electron, and here this electron has to be oppositely spin electron. Oppositely spin electron here can overlap with oppositely spin electron. Okay, and this results in chemical bonding. Number 2 point: when atomic orbitals of each atom overlap, then then this results in molecular orbital or covalent bond. Okay, and you have to remember, once they overlap, these atomic orbitals, they overlap to form molecular orbital, or we can also say covalent bond. Then you have to remember the energy of this molecular orbital is lower than the atomic orbitals of the atoms. And the third one that you have to remember is greater the overlap, stronger will be the bond. Stronger will be the bond, the covalent bond or the bond. Okay. So overlap. So let's discuss about. Last time also we had discussed. Suppose this is s orbital and this two s orbital. S orbitals are spherical in shape. So whenever there is this bond formation, what happens is they come close together and they overlap. And this region, which is common to both of this s orbital, is the region of overlap. This is the overlap. So greater the overlap, if you have greater overlap between these two orbitals, then the bond will be stronger. Now here, molecular orbital, atomic orbitals, they result in molecular orbital, and these molecular orbitals are of two types, and one is sigma bond, the other one is pi bond. And we had discussed about sigma bond and pi bond in our previous video also. So you can refer to that, or you can go through the book. Okay. Now let's move on to the next topic, that is dipole moment. Now we are going to discuss about the next topic, that is dipole moment. Now here, dipole moment, what does it mean? Dipole moment of a molecule. Okay. Now going to its basic definition, you can write it as dipole moment, which is represented by mu is equal to the either of the charge. It could be either positive charge or the negative charge. Okay, the total charge into the distance between these charges. So mathematically, dipole moment is equal to either the positive charge or the negative charge into the distance between them. So in this statement, okay, stating it, let's listen to it. Dipole moment of a molecule is the product of its net positive or negative charge and distance between the charges. So mathematically we can write it as this one. Now here, what you have to remember is dipole moment in diatomic molecule. So what does it mean? So let's discuss about that. Let's take di molecule HF. Now in this HF, this is a covalent bond. This is a covalent bond. This is formed by sharing of electron. And here, the electronegativity difference between hydrogen and fluorine is not same. It has, the fluorine is more electronegative than hydrogen. Therefore, what will happen? Instead of those electrons remaining exactly at the center between this hydrogen and fluorine, it is pulled towards, it is shifted towards fluorine. As a result, it has delta negative charge and it has delta positive charge. Now, the element which is more electronegative, you can see that it is, instead of the electrons lying exactly at the center, it is pulling towards itself. Now this type of pull is denoted by this arrow because it is in this direction, and the dipole moment is represented with an arrow towards the electronegative atom with this sign. Okay? Now, since you have only one bond in this particular molecule, it is pointed towards what? Fluorine, and it has a net dipole moment, which is not equal to 0. That means it has some net dipole moment. Now, this net dipole moment is itself the net what? Dipole moment of the molecule. I mean to say, since you have only one bond, yes or no? One bond. Now, this one bond itself accounts for the total dipole moment of the molecule in a dimolecular compounds. Now, let's discuss about more complex compounds. Where now, if you have, say, let's take another example, triatomic molecule, carbon dioxide, and say water molecule. Now, here you don't have only one bond in carbon. You have what? You have carbon is doubly bonded to each other, oxygen, and water, as you know, water molecule, you have oxygen which is bonded with hydrogen, another hydrogen, and it also has lone pair of electron. So now, depending upon its structure, their dipole moment will be different. Now here, in carbon dioxide, oxygen is more electronegative than carbon. This side oxygen is more electronegative than carbon. Now this side, you have dipole moment. Now whenever you consider this carbon and oxygen bond only, then it has a net dipole moment towards oxygen side. And this side, if you consider, then it has a net dipole moment towards this oxygen side. Now, since they are having what? They are having dipole moment in opposite direction. Now here, it is individual bond moment. Okay? It is having in opposite direction, and you can see that it is exactly equal in magnitude. Why equal in magnitude? Because the same oxygen is present on the both sides of the carbon. Therefore, individually, they will be having what? Bond moment. But this molecule as a whole will have dipole moment which is equal to 0. Why? Because this side pull will be cancelled out by the pull on the right hand side. Okay? Now let's come to this oxygen water molecule. Here, as you know, oxygen is more electronegative than hydrogen. Therefore, each bond moment will be towards oxygen side. And as a result, now since this side is both in the same direction, and this water molecule will have a net dipole moment in the upward direction. And its dipole moment is not equal to 0. It is around 1.84 D. 1.84 D. Okay? So this was the application of dipole moment. From that moment, you can predict the structure. This is linear structure. And this is having what? You can see it is V-shaped. V-shaped or bent. Okay? So mostly such type of questions will be asked from this type of moment topic. Now let's move on to the next topic, that is polarizing or polarizing power, and under that we are going to discuss about Poisson's rule. Now we are going to discuss about polarizing power or polarizability, risability. Okay? And under that we are going to discuss about Poisson's rule. Poisson's rule. Now, what does polarizability mean now? For that, let's have a look at this particular sample. Here, suppose this is a positive charged ion, and here it is what? Negatively charged ion. Now, whenever they come very close to each other, then what happens? The shape of the anion gets deformed, and here positive charge is present and most of its negative charges will be lying towards this side. This is because this force of attraction. Now this distortion caused by this positively charged cation in the shape of the anion is known as what? It's known as polarizability, and the power to do so is known as its polarizing power of the cation. Now this polarizability is governed by what? Hudson's law. Now there are certain factors which affects polarizability. Okay, so we are going to discuss about factors affecting polarizability. So the first one is the size of the cation. Size of the cation. Now here, is smaller the size of the cation. If the size of the cation is small, then what will happen? Its capacity to distort the anion will be more. Therefore, we have to remember, smaller the size of the cation, greater will be polarizability or polarizing power. Polarizability or polarizing power. Similarly, if you have a large size of the anion, then the polarizability will be more. Okay? So the second point that we have is larger the size of the anion, greater will be it will be larger size of the anion, it will be polarized or distorted, polarized to greater extent. Okay? And the third point is if you have a large size, not the size, if you have large charge on both the cation and anion. Okay? The third point is large charge on both cation and anion. Now, if the charge of both cation and anion is large, that means there is more interaction, they will be attracted to each other to more extent. Therefore, polarizability will be again greater. If the charge on both of this positive ion and negative ion is high, then polarizability will also be more. Now, what you have to remember is the fourth point is presence of medium. The fourth point that we have is presence of medium. Presence of medium. Okay? Now, this particular point is very important. Now, please listen carefully. If you have certain polar solvents like water, okay? Water is a polar solvent. Now, in presence of polar solvent, those compounds which are covalent in nature, in presence of this polar solvent, they will be acting as what? They will be behaving as ionic compound. For example, AlCl3 is what? Covalent compound. If we don't have what? Water as the medium. Now, whenever this AlCl3 is present in the water, then it behaves like ionic compound. It behaves like what? Ionic compound. Now, these are the points that you have to remember from this particular topic, that is polarizability and these 4 points are very important, okay, and in deciding the covalent character of ionic bond. So this was for today. We will be discussing about variable covalency in our next video. Till then, keep revising. Okay, thank you.